In this video, we'll complete the integration of the trigonometric function with different powers. In video number part 1, we speak about how to integrate the trigonometric functions and the hyperbolic functions if the power is 1, and also how to integrate trigonometric and the hyperbolic functions if the power is 2. And we spoke about the case in which we have cosine, sine, sine, cosine with different powers, and we have the case if the power is odd and the case if the both powers is even. In this video, we will discuss the case if we have the product of tan x to the certain power m times sec x to the certain power n. Of course, tan times sec or cotan x times cosec, and the same if we have tanh times sec or cotang times cosec. The idea is tan and sec is related by the identity that 1 plus tan squared is equal to sec squared, and also 1 plus cotan squared is equal to cosec squared, and the derivative of tan x is sec squared, and the derivative of cotan x is negative cosec squared, and the derivative of sec x is sec tan, and the derivative of cosec x is negative cosec cotan. So you can see that the tan and the sec functions are related by the identity, but take care that this identity is using the square, so it needs even power to transfer between the two functions without roots. And also the derivative of tan is sec squared, and the derivative of sec is sec tan. So if we have an integration of product between tan to the power and sec to the power, we can think about we can have the derivative outside, which is sec squared in some cases or sec tan in another case. Let's see for this example if we need to integrate sec power 4x times tan power 4x. Because the power of sec here is even, we can rewrite sec power 4 as it is sec squared times sec squared. And we need this sec squared to be the derivative, and of course changing the remaining sec squared to be tan, because sec squared here is the derivative of tan. So we can have this sec squared beside tx, and the remaining sec squared can be changing to tan, as sec squared is 1 plus tan squared, and we have still tan power 4 multiplied. Now we have sec squared, which is the derivative of tan, and all the other term is tan to the power, so we can easily using the power rule after expanding. So the first case here, if the power of sec is an even power, we can take sec squared to be the derivative, and the remaining power of sec, which will be even also because we took sec squared, we can change it to tan and use directly the power rule. So if we expand tan power 4 inside the bracket, we will have tan power 4 plus tan power 6 times sec squared. And of course the first integration term, it will be tan to the power 4, and the derivative of tan is sec squared. So directly applying the power rule, it will be tan power 5 over 5. And second term we have tan power 6 multiplied by sec squared, so it will be tan power 7x over 7 plus c. So the first case here, if the power of sec is even, we can take sec squared to be the derivative, and the remaining even power of sec can be changed to tan. Let's see this case if we need to evaluate the integration of sec to the power 5x times tan to the power 3x. In this example, the power of sec is to the power 5. So if you think you need to take sec squared, the remaining from sec will be sec power 3. And if we change sec power 3 to tan, you will have a root and it will complicate the integration. So it will not work. But because the power of tan is odd, if we write this tan as tan power 2 times tan, and having this tan to be the derivative, but the remaining tan squared will change to sec, and the derivative of sec is sec tan, so we need sec from sec power 5. So we take also from sec power 5 sec, then the remaining will be sec power 4 times tan squared. Please don't be confused that whatever the remaining of sec, we are only need the remaining of tan to be even. To change it tan squared, it will be sec squared minus 1. Because the derivative here, sec tan, is the derivative of sec, so we need all this function to be sec to the power. So after changing tan squared, it will be sec squared minus 1. Expanding sec power 4 inside the bracket, we will have two terms, sec power 6 minus sec power 4. And outside we have the derivative, which is tan x sec x. So now we can use directly the power rule, because in the first integration we have sec power 6 and the derivative of sec, which is sec tan. So the integration will be sec power 7 over 7. And in second integration we have sec power 4 and its derivative of sec also is sec tan. So integration will be sec power 5 over 5 plus constant. So you can think now that the second case, when we have a product between sec and tan, if the power of tan is odd, we can easily take sec tan to be the derivative and change the remaining tan to sec, and then applying directly the power rule. Of course you think now, what if the power of sec is odd? So you could not take sec square. And if also the power of tan is even, so you could not take sec tan. Let's see, in case of that we have sec x times tan squared. The problem here is that the power of sec is 1, not even power, and the power of tan is 2, not odd power. In this case, my advice is to change tan, which is an even power, directly to sec. So tan is sec squared minus 1. So all the integration will change to sec power cube, sec times sec squared, minus sec x dx. And then we use integration by part if we have higher power for sec with an odd power. So for the integration we have now two terms. The first term is sec power 3 and the second term is integration of sec x. Of course the integration of sec x, which is the second term, we discussed this in the last video, that the integration of sec is ln sec plus tan. And the video of the integration by part, we discuss how to integrate sec cube by part twice, and we return it's the same value again. So let's say that this integration is called I1. So we have I1 as the integration of sec power 3, And if we write sec power 3 as sec x times sec squared x and use integration by part, we will have select u as sec x and the dv as sec squared x dx. We will have du as a derivative of sec, which is sec x tan x, and the integration of v, it will be tan x. Now I1 will be u times v, which is sec x tan x, minus integration v du, which is sec x times tan squared. And of course tan squared can be written as sec squared minus 1. So I1 will equal to sec x tan x minus integration of the first term, it will be sec cube, and second term, it will be integration of sec. Of course, sec cube here is the same form of the integration I1, so we can write it at I1, and to collect I1 in the same side, we will have 2I1 equal to sec x tan x plus integration of sec, which is len sec plus tan. And now we can write I1, it's half time all this term plus constant, and we can put I1 value minus this integration. We will have our integration for sec power 3. So in this case, if we have the product between sec and tan with the power of sec out and the power of tan is even, we change all the integration to sec to the power by changing the tan, which is an even power. And then if we have sec to the power 3 or 5 or 7 and so on, we use integration by part to evaluate this integration. To sum up the cases, we spoke about the integration of tan to the power times the sec to the power. And the same is about if we have cotan to the power times the cosec to the power. And also the same for the hyperbolic tangent sec or cotangent cosec. Case number 1, if we have the power of sec, which we named here by n, is an even power, we can easily take sec squared to be the derivative and changing the remaining sec to tan and using the power rule. Case number 2, if the power of tan is odd, that the power of tan is odd, we can take sec tan to be the derivative and changing all the remaining to sec and using the power rule. Case number 3, if the power of tan is even and the power of sec is odd, so we change the tan to the power to sec and then use integration by part. We change to sec and then use integration by part. That is the 3 cases we can see when we have a product or integration of tan power times sec power. Now finally, let's see the case if we need to integrate cosine 3x times cosine x dx. Of course, we have the product between two cosine functions with different angles. There is an identity that change cosine A times cosine P, change the product to plus. It's a half. If we have cosine A times cosine B, it's a half cosine the sum of the two angles. plus cosine the difference of two angles. The same if we have sine A times sine B, it's half cosine the difference A minus B minus cosine the sum. And the same if we have sine A times cosine B, it's a half sine the sum plus sine the difference. These identities can change the product between sine, cosine, cosine, sine, or sine, cosine to a sum, so we can integrate easily. So in our example, we have cosine 3x times cosine x. So if we think about this identity, our integration will be half cosine the sum, which is 4x, plus cosine the difference, which is 2x dx. Now half is outside, and the integration of cosine 4x, it will be sine 4x times 1 over 4 plus cosine 2x, it will be sine 2x times 1 over 2 plus c. So if we have the product between cosine cosine or cosine sine or sine sine with different angle, we can use these three identities to change the product to a sum and then integrate. Thank you.